Last time I had this talk was in Krakow, and it was at 9 p.m. So most of the people were actually half asleep. So it's good to see like people awake after. I know it's after lunch and glucose levels are high, but I bet the flows and coroutines will keep you awake, guys, because flows are a really cool thing, and even better, they are like a cherry on top of another really cool thing. But before we get to that, let me tell you a story of Mark and his space exploration, which hopefully is going to be less tragic than that of Tony Stark's space exploration. I hope I haven't spoiled if someone hasn't seen the latest Avengers. Definitely recommend, one of my favorite movies. I've tortured my wife to see all the Avengers movies with me. So I bet she must love me. Anyway, it's the year 2047, and Mark is the captain of Leto 2, the second expedition to Mars. And the first expedition disappeared mysteriously, having launched from Phobos, one of the satellites of Mars. And Mark has traced Leto 1's steps all the way from Earth, Moon to Phobos, and he was supposed to discover what happened with these guys, right? But he hasn't seen anything. He hasn't faced any complications yet, and that's what worries him most, right? Because he's traveled quite a way from Earth, and he should have some ideas about what might have happened, but he's seen nothing. And now that it's time to launch from Phobos and attempt to land at Mars, he's pretty nervous, and he hopes for no unforeseen complications. And Leto 2, same as Leto 1, is traveling on board a large carrier, which has massive engines, and these engines take quite a while to start. There is also an auto-cleaning system which is supposed to preserve these engines, which also takes quite a while, right, because the engines are large. And to save time, both of these are executed asynchronously. And this is the code that controls all this stuff. It's the same code that was used by Leto 1, right? So what we are doing here, we are introducing this asynchronous logic using Java's completable features. We simulate some heavy work and return the value which corresponds to the maximum value at which the ship, the engines, can go. And this is the auto-cleaning function, which, to have some fun, simulates a failure, right? So it simulates some work and then throws an exception. And this is the driver code, which at the first glance looks more or less fine, right? We start both of these asynchronously, start the engines and the auto-cleaning system. We grab the futures, we print a log that the futures have started, and then we want to set off at the maximum speed that the engines can go, and we want to report the result of the auto-cleaning system, right? The problem here, though, is that futures are known as hot sources, which means that you basically need to look after them just like they were resources, like an open file. You need to make sure to clean up after yourself. You need to close these resources. And here, these two futures are completely unrelated, right? One doesn't know of the existence of the other. And in this scenario, two bad things may happen. So, first of all, you might leak the subscription to your first engine future if the second future fails, right? If it throws an exception, you'll quit the method, and you won't have the reference to the engine future anymore, which is pretty bad because it will just keep on running in the background, right? And the second bad thing, even worse, that might happen is that if this guy then, engine future, throws an exception, you don't have a reference to it anymore, so you can't handle this failure, right? There is nothing you can do with it anymore. So let's see what happens when we run this guy. We'll get the print statements from these futures. We've got a log printed somewhere in between, which shows that we are running this code indeed asynchronously because the logs are printed out of order. Then we're gonna take off, right? Our spaceship is happily drifting away from Phobos, and then damn, the auto-cleaning system fails, the engines are on fire, everyone is shouting and running in panic, and it's too late to do anything, and we are just happily drifting into an unstoppable explosion, probably. And maybe that's what happened to Lita 1. Maybe we've helped Mark solve the mystery. Well, now let's see if we can do something about it. Let's see if we can save Mark, and let's see if we can help this poor guy out, right? We don't want to blow everyone up. What we can do is we can use combinators, right? If someone is a hardcore Java developer, then you might have used something like that, right? Combinators, as the name suggests, basically allow you to combine futures. And now they are aware of one another, right? You run your first future and then you say combine, and then if everything is fine, then you set off. If not, you'll cancel the futures, right? And that more or less is fine, right? What happens here is we get the print statements, and then we get the exception printed, but this spaceship has not left, right? So we've got time to extinguish the fire, which is pretty good. The problem is that if you look at this code, I wouldn't call it the prettiest code I've ever seen, right? I don't know. I mean, it's probably down to personal preference, but I would say that calling this guy spaghetti code is like calling the hole in the train a toilet. I mean, I'm glad that they are bringing pendolinos here, because like whenever I go to the toilet in a train, I'm afraid that Gerek's face will jump out at me. What might help us out here is some Kotlin stuff, Kotlin coroutines. Let's see how this might help Mark, and more importantly, how's this going to help you to write asynchronous code that you are familiar with, right? Without combinators that you really need to go deep down into, and second of all, you're pretty lucky if you've got the combinator that you actually need, right? So let's see how you do it with Kotlin coroutines. So first of all, we'll modify the spaceship functions. They're not going to return the completable futures from Java. They're going to be suspending functions, which is some Kotlin magic. We're going to explain in a second. So first of all, you'll probably notice that we've got this suspend keyword, which declares the function as suspending, right? Now, what we need to do is not only declare this function as suspending, but actually make it suspending, right? Before we do that, though, you're probably asking yourself, what is a suspending function? What does it mean that a function is suspending? Well, it's a pretty cool term, which basically means that the function's execution can be paused and resumed at a later time without blocking the calling thread, right? So you get true asynchronous behavior. And how it works under the hood is that this suspend keyword will be translated into an additional callback continuation parameter, which will be used by the, whatever you call inside, whatever you're waiting for. If this guy is ready, then he's gonna, kick the callback and say, hey, I'm ready, we can continue, right? So pretty easy mechanism. If anyone is familiar with JavaScript, you've got callbacks there. The good news here is that you don't need to manage this callback hell yourself. This is done automatically for you just by using these suspending functions. Now we also need to change the second function, which instead of returning a deferred of Boolean, just returns the value itself. Sorry. But you're probably asking yourself now, what is this with context thing, right? We didn't have this before. What does it do? Well, that basically does the suspending magic. What this guy does is it calls the block inside the curly braces. It suspends and waits until this guy inside finishes its execution. It also takes an implicit parameter, which is coroutine context, and in our case, this is a dispatcher, which allows you to basically define how you want to run your computation, right? We've chosen an I/O dispatcher because we know this is not a CPU-intensive task. You just kick off some computation, you need to wait. This is exactly what I/O is, right? If someone uses Rx Java, you've got something similar there. You can define your scheduler as I/O and wait for some resource to basically give you the data, right? This is something similar what we're doing here. And wow, look at this. With coroutines, we almost went back to the original example, right? You can write your code as if it was sequential, and this time it'll actually be correct, right? It's very easy to write and it's super readable, right? You can reason about it just like you did before. You know what you want to do there, right? With the example before, with the combinators, you had your spaceship set off somewhere embedded in the very middle, right? If you just look at it, you're like, God, what's happening here, right? And now you just look at this guy and you know what's happening, right? This is very familiar code to every developer. Yeah, well, this is for, I guess, you know, pretty well-known sequential code as well. What you get here is you've got your coroutine scope. Everything is inside this coroutine scope, right? And this is the guy that does all the magic for you. This, I don't want to go too technical, not to bore you to death, but basically this guy has two important properties. First of all, coroutine scope waits for all its children to finish before finishing itself, right? So that basically allows you to reason in a sequential manner about your code. And second of all, if any of this coroutine scope children fail, then all of the children will be cancelled, right? Which is exactly what we want, right? If the second coroutine, the cleaning deferred guy fails, then we don't want to set off with our engines on fire, right? And it's pretty cool that in Kotlin, you're not allowed to launch a coroutine outside of the coroutine scope, because Kotlin's developers really want you to be explicit. They want your concurrency to be explicit, right? So you don't need to manage this manually. This will be all done for you. Now, where are these coroutines and what are they? Well, they are right here, right? And they are basically like lightweight threads. You can think of them as lightweight threads. So lightweight, in fact, that you shouldn't only be afraid to create many of them, but you're actually encouraged to create many of them to structure your concurrency. You're encouraged to create these tiny coroutines which run in a well-defined context, because most of the time, the idea of Kotlin developers is that most of the time you actually want to run your concurrent code in a well-defined context, right? Sometimes you need to have some multi-threaded, like some operation running for a long time in another thread. You can do that too. But here, we just want to spin it up for a while and then just clean up, right? And that's what coroutines really allow you to do. I guess this really shows you how easy it is to create these guys, right? You just wrap your suspend function in an async block, and that's it. You've got your coroutine. Yes, they'll run concurrently. Right, but yeah, yes, that's the whole idea. And async is basically like looking slightly under the bonnet. Async, this modifier here, is an extension function on the coroutine scope that we see at the very top. Again, if someone doesn't know what extension functions in Kotlin are, it doesn't matter. It basically operates on the coroutine scope, right? So this is related basically to this coroutine scope. And coroutine scope handles cancellation for you. So deferred is failsafe, right? And notice that we are returning here engine deferred, not engine future. Deferred is basically like Java's equivalent of completable future. In Kotlin, we've got deferred. But again, this time, this is going to be correct because we've got this coroutine scope that looks after us, right? And all these guys, being slightly more technical for a second, all these guys create their own coroutine scope, which basically allows you to create a separate job for each of these so that they can run concurrently. Each of them will be run separately, but they all will inherit a coroutine context, which is the guy that will actually propagate your cancellation. So if your child fails, then you'll want to cancel the parent as well. Or in our coroutine scope that we saw with toDeferred, if you cancel one of the children, then the others will be cancelled as well. Cool. So we've helped Mark find the possible cause of what happened to Lita 1. More importantly, we found a pretty good way to decompose our computation in parallel, which is good for us as well. So now Mark is off from Phobos. He's going to continue his mission, and he's going to attempt to land on Mars. But before he does that, you know, it's a pretty new thing, right? Landing on Mars. So before you just happily try and jump on the planet, it might be a good idea to do a reconnaissance flight, right? So what Mark is going to do is he's going to fly around the planet and collect some measurements. This is the first attempt of what the engineers prepared for him. So there are quite a lot of sensors on the spaceship, and we'll want to collect the readings from all of them. And they all take a while, right, to read the reading. We've got some thread sleep simulating processing the data, and then we're going to return all of them in a list, right? And what Mark actually wants to do is he wants to fly around the planet, and obviously he's flying on autopilot, right? This is not a Fiat 126P. And there is quite a lot of debris, right, outside of Mars, right? If anyone follows, NASA is not the cleanest company, right? They are leaving quite a lot of rubbish everywhere in the outer space, and there is quite a lot of debris around Mars as well. So we've got our autopilot, but we can't just set a route once, right? We need to constantly keep on correcting the path, not to fly into any of the rocks or any trash, right? So we want to have our autocorrection running all the time, and then kind of separately, right, asynchronously, if you will, we want to start collecting these readings and process them one by one as they arrive, right? And processing them will mean Mark looking at them personally, right? Because he's pretty nervous and he doesn't want to trust the computer. He just wants to approve the reading manually, and if it's fine, we're going to continue the reconnaissance flight and eventually attempt to land on Mars. If any of the readings is like out of bounds, right, our spaceship has not been prepared to withstand such conditions, then we're going to cancel, right? We're not going to crash attempting to land in the conditions we are not ready for. So this is our first attempt, and first we've got this is our first coroutine. Launch is another builder for creating coroutines. So we've got our first coroutine, which simulates this autocorrection, right? We're just gonna keep on printing that we are correcting the path and waiting for a while. And this is a little hack, right, that I had to introduce because this guy will obviously start, because it's asynchronous, it'll start executing constantly. So we want to wait for a few of these print statements to print out before we actually start collecting the readings, right? And how we're going to do that is we're going to ask for all the readings, iterate through all of them. We've got a sleep which simulates marks validation, and then we're going to print what the reading is, right? And let's see how that works. That's not great, right? We've actively corrected path for a while, and then it blocked, right? Everything just blocked when we started collecting the readings. And also, we only process the readings when they all arrived, right? So we are not doing at all what we are supposed to do, right? First of all, we've blocked the main thread. Second of all, we are not processing the readings one by one as they are coming in. We're processing all of them when they are ready, which is not cool, right? Because we've got 2 readings here. Imagine we've got 100, right? Or 1,000. So that's not cool. We might crash, right? And fly into some NASA rubbish, which will be quite sad, probably. So what's going to help us out? Suspending functions. You've guessed it. There you go. So again, what we want to do is we'll declare all these reading collecting methods as suspending. They'll all be suspending. And now what we'll do is we're not going to return all of these in an eager list, right? What list needs is it needs a list of well-defined computed values, right? What we'll use is we'll use a flow, right? And what is a flow? A flow basically is a cold collection, right? Which means that it's not going to bind any resources. It's not going to wait for all the values. It will allow us to process the values one by one exactly as they are coming in, right? Nothing is going to happen just when it starts. So let's see. Let's see how that works. So we've got our emit function inside the flow. And I guess this is like not the best name, because if you look at the documentation of emit, it says it declares the value as being available to the collector later, right? So, well, I guess emit is not the best naming, because it doesn't actually emit anything. It says that these values will be available in your flow later when you actually want to do something with your flow. So let's modify our code, and this time we're going to get all the readings in a flow, not in an eager list. And this time we are not really iterating through them. We are executing collect operator on the flow, right? Which is called the terminal action. And this only triggers the execution of the flow, right? Up until this point, nothing has happened, right? No reading was executed. No, there are no values in our collection. only when we call collect, then we start executing action, which is the block inside the curly braces. Only then will we start executing this action on each of these elements when they start arriving. So let's see how that works. We've got our correction running all the time now, right? And then there we go. One reading comes in, another reading comes in, and then we've printed it one by one, right, as it was coming in. And if you notice, on the third line, we've printed the flow, right? But what doesn't print? Well, not much. It prints like a memory reference because there is nothing to print. We've only kind of created a placeholder for the collection and for the values, right? There are no values in it yet, right? So, have we just created Rx Kotlin, right? Why should Mark care? Why can he just not use Rx Java in Kotlin, right? We've got interoperability. Why should he care? Why should you care? Well, for Mark, for sure he could care because he's pretty far from home, right? Houston is pretty far, and it makes a ton of a difference if you can actually fix something yourself, right? If you can improve the tools in your toolbox, right? If you can look under the bonnet and see how it's working, but more importantly, if you can create your own tools, right? If anyone has tried that in Rx Java, that's not an easy task, right? It's actually pretty difficult, and you're not advised to write your own operators. It's pretty difficult. You've got this massive contract, pretty difficult contract that you need to stick to have a properly working operator. Partly the reason for this is that there is no like kind of first-class support for back pressure on JVM, right? So you basically need to simulate it yourself, right? You need to write the code that simulates back pressure. And how flows work is pretty cool because they work using suspending functions and coroutines, which is pretty cool because it's super easy. It is built only using, well, in the simplest form, 3 elements. So first of all, we've got our flow interface. And this flow really has only one method, one function, which is called collect, right? This is the terminal operator that we've seen at the very end that triggers the entire flow, triggers the execution. And this guy accepts a flow collector, right? You pass out a flow collector. So what is a flow collector? A flow collector is an interface that has a single function as well, which is a submit function, this poorly named function, which basically declares the values being available later, right? So you've got these two, and you can create your flow, really. You can declare your values as being available, and then you'll just collect them at the very end. And because all of these functions are suspending, or rather suspendable, you can suspend them, pause the execution, that gives you back pressure for free, right? Because if you're executing too fast, then you're just going to suspend the function. If you are executing too fast, as in you're consuming too fast, then you're going to suspend the function that is actually executing, right? You can wait for more values to come in. And if the guy produces too fast, then you'll just indicate to this guy that you are not ready to consume via suspending function. This guy will suspend himself and wait until you've consumed all the values and you're ready to accept some more. And what does this collect actually look like, right? Because we haven't created a flow collector, right? We've just called collect, and we have these curly braces. So how does it work actually? Well, this is how it actually works. We've got this collect method, which has this funny extension function syntax from Kotlin, which means that you're calling it on a flow of any value. And by default, this guy creates inside a flow collector, which overrides this funny emit function by calling an action upon each of the elements, right? Emit has a value, and you call an action on it, An action is whatever you define in these curly braces, right? Which is exactly what we did. And flows are pretty cool because they follow the entire logic, the entire principle of Kotlin language, which is, well, one of them, extension-oriented design, which means that you should be allowed to extend whatever there is yourself. You should be able to add your stuff to it, right? And with flows, it works exactly like that. You can really easily create your own operators, right? And at the first thought, you might think, why on earth would I want to do that, right? I'm pretty happy with my RX Java. I've got a few of my functions. Why would I want to do that? Well, one reason is that you can define your operators with your own domain logic. We can create a validate measurement extension function which works only on the flow of type sensor reading. It's aware of the values that we are processing, right? So we can have some domain logic in there, right? And again, writing this is pretty simple because we've got a transform function which is given to us by the Kotlin developers, which is designed exactly to create your custom operators. It's supposed to be used as a building block, basically. And again, because we are actually inside this flow now, we're actually operating inside the flow collector. Sorry. And now we can just use this validate measurement just like it's an ordinary operator, right? No difference between the ones that you were given originally and the ones that you write. They are first-class citizens. There is a little detail here. If someone is a keen observer, maybe you've noticed. If you compare this to RX Java, if anyone has RX experience, there are no subscriptions, right? And why is that cool? Because you cannot leak a subscription, right? Subscriptions are resources that you need to manage yourself as well. You can leak subscriptions, and bad things may happen, right? So it's better not to have them and not have to worry about them. And with flows, that basically means that you've got your flow, right? First, we get all readings and flow, then we validate them, and all the time, when we ask the compiler to show us the type, all the time we've got this flow, right, of sensor reading, until we call this terminal action, right? And then when we've called this terminal action, our collect, then what we get at the end is a unit. No subscriptions, no more flows, no cleaning up, right? Everything was done automatically, and we don't need to worry about any resource management or anything, right? That was all done for us. So it's really super safe. And one more thing, which is pretty cool, is error handling, right? We've got this .catch operator, which is, it's called exceptionally transparent, right? It's a fancy word, sounds pretty complicated, but basically what it does is it catches the exceptions upstream, right? It doesn't catch the entire stream. It doesn't kind of, it doesn't destroy the logic of your entire flow. It basically works on what's above the sky. And you can obviously create your own exception operators as well, right? So we can define a custom error handler, which this time we're going to write a generic guy, so you can hook it into any flow. But again, this guy can be aware of our own type of exception, right? If we get an exception that is really not cool, and we really don't want to see these kind of exceptions, then we're going to send an email, right? And you can just encapsulate this logic and use it as a first-class citizen operator. And what's pretty important for Android developers is that just like with coroutines, you can change the execution execution context of your flow, right? And obviously you've got an operator for it, right? You just change the dispatcher. So say you're an Android developer, you're writing your main kind of UI window, which runs in the main thread, and you need to do a network call, right, to get some data, and then you'll want to display it. Obviously, you don't want to freeze your UI while that's happening. So what you might want to do is you want to throw this computation over to an I/O dispatcher, which exactly does what it's supposed to do, right? So it just throws the calculation, and it waits until it's available. Then it carries on, and then after this flow on, again, we are back to the dispatcher that we were on previously, right? So you don't need to manage this yourself. This flow on only works for the app stream as well. What would be quite nice, which was my first thought when I was looking at flows, was, oh wow, that's really cool. Can I just process it concurrently in parallel? Well, the answer is no, you can't, at least not now. What's supposed to come later is this new operator called concurrent, where you'll just define how big your pool you want to have, right? And then this pool of workers will concurrently pull the values from your flow and process them concurrently. This is not the best design though, because you've got these two collects, and you're really wondering, oh God, what is happening here? Why do I have two collects? Which one actually works? Well, the answer is that actually the first one works. The first one actually does your processing, but because it's inside concurrent, it's like working on a different object. Then you need to have your terminal operator on your flow, and you need to attach one more collect at the end, right? So it's not the best design. I hope they'll come up with something better. Cool. So thanks for your attention, guys. My name is Krystian Rybarczyk, and I enjoy searching for what's best in the JVM world. So I enjoy actually looking at different JVM languages. Here is the presentation and the code if you guys want to have a look at it. Don't hesitate to get in touch with me on GitHub or on LinkedIn. Do send me a message. I'll probably be around after the talk as well, so if anyone wants to talk in person, then do come over. And if someone is a keen observer, you might have noticed I work for a company called Codete, which is one of the sponsors, I believe. We've got a booth on the first floor, so come and say hi right next to the main stage. And we do some pretty cool stuff. We've got two offices. The main one is in Krakow, and then we've got a smaller one in Lublin, but it's a pretty cool one. We don't sit in a garage, so it's not bad. We've got quite a lot of employees now, about 150 people. And again, what's pretty cool is that most of us are developers. There is pretty thin management. There is no hierarchy, as in we've got a really flat structure. And we've got quite a lot of projects for small and for big companies, whatever you fancy, and a ton of technologies, back-end, front-end, DevOps, full stack, whatever you fancy you'll probably find there. And we do organize some events and meetups. So there was one Codete Con in Krakow. There will be one in Lublin, apparently, in the new year. We do organize Shit Happens events in Lublin. And there is an AI meetup because being a tech company, one of our founders is actually tech, and he does AI. So it's I don't know. I was pretty excited about it when I came over. So do come and say hi, or if you're more of an introvert, have a look at the website. Thanks for your attention.